Hey, I'm Fleshed Out Thoughts, and I love fleshing out thoughts for extended periods of time. I'm building a full stack e-commerce platform for digital products and software services with Next.js and Supabase. This series is about the architectural decisions behind the platform, what I built, why I built it that way, and what I do differently. Today, we're going to be getting into database design for Next.js, e-commerce platform, Postgres, Supabase, and schema decisions. Every feature I've talked about in this series, API contracts, authentication, authorization, state machines, all of it sits on top of one theme. That is the database. Get the schema right, and everything else gets easier. Get it wrong, and you'll be fighting your own data model for years. Here's why schema decisions are different from other architectural decisions. They're expensive to reverse. If I chose the wrong primary key type, migrating it means touching every table that has a foreign key reference to it, which could be most of the schema. If I chose the wrong column type for timestamp, I'd need to rewrite every query that uses them. If I forget a constraint and bad data is now in production, I have to clean it up before I can enforce the constraint. Application code you can refactor. Database schema carries data, and that data has to migrate with them. I'm building a full stack e-commerce platform for digital products and software services with Next.js and Supabase and Postgres under the hood. This video is about 3 decisions I made before writing a single migration. UUIDs on every table, JSONB for blog content, and constraints at the database layer. The schema has 9 tables. I'll walk through all of them. 1 database until measurements prove otherwise. My platform needs 4 things from its database: ACID transactions for orders and payments. A double charge or missed inventory write on partial failure is real money lost. JSONB for flexible blog content blocks and product attributes. No separate document database needed. Full text search for posts and products. Updates in the same transaction. No asynchronous indexing pipeline. No eventual consistency lag. And row-level security for multi-user data isolation enforced by Postgres on every query regardless of what the application code does. The principle behind this choice? 1 database until measurements prove otherwise. Every additional database you introduce is a new failure mode, a new consistency boundary, and a new operational burden. If I added MongoDB for blog content, I'd need to keep it in sync with Postgres. If I added Elasticsearch for search, I'd need a pipeline to populate it and handle consistency lag. Each addition multiplies your surface area for failures, and you own all of them. JSONB replaces MongoDB. tsvector replaces Elasticsearch. RLS replaces manual auth checks in application code. 1 database, 1 backup strategy, 1 thing to monitor. The core schema, 9 tables. Here's the actual schema. 9 tables in 3 rows. Row 1, profiles, orders, order items, products. Row 2, carts, cart items, coupons. Row 3, notes, the blog post table, and order events. 2 normalization decisions that aren't obvious from the diagram alone. Order items is a separate table rather than a JSONB array on orders. This matters for queries. If it were a JSONB array, computing the order total requires unpacking JSON in SQL. Awkward and slower, right? With a separate table, I can write select sum price times quantity from order items where order ID is 1. A clean indexed aggregation. Line items are independently queryable. Which products appear in the most orders is a simple group by on order items, not a JSONB unpacking exercise. Order events is a separate table rather than a history column on orders. This enables index queries by event type and timestamp. All payment failures in the last 24 hours is select all from order events where type is payment failed and created at greater than now minus the interval 24 hours with an index on type created at. Storing that history in a JSONB column would require scanning every event in every order and unpacking the array. Every table has a UUID primary key. Every timestamp uses timestamp Z. Every foreign key has an explicit on-delete behavior. RLS, which table needs it and why. The green tables, profiles, orders, order items, carts, cart items, have RLS enabled. Users see only their own rows. Blue tables, products, coupons, notes, order events are either publicly readable or scoped differently. I covered RLS in depth in the authorization video, so I'll add one thing here that belongs in a database design discussion: performance. Every RLS policy adds a predicate to every query against that table. Simple policies are fine. Auth UUID is user ID, is a single lookup against an index column that is effectively free. Complex policies, such as one that call functions, do subqueries, or join other tables, can slow down queries noticeably because they execute on every row evaluation. So the simple rule to follow: I keep RLS policies simple. Indexed predicates. If your policy needs to be complex, that complexity should live in a function that is efficient and testable, not inline in the policy definition. My policies are all single condition comparisons. That is deliberate. UUIDs. Why not serial integers? Every primary key is a UUID, not a serial integer, not a big int, a random 128-bit value. There's 3 reasons to favor UUIDs. First, UUIDs are safe to expose publicly. Order IDs appear in URLs and confirmation emails. Sequential integers let anyone enumerate your order volume. A competitor creates an order, sees they got ID 847, and now they know your approximate sales count. UUIDs make enumeration impossible. Secondly, UUIDs are globally unique without database coordination. I can generate them in the application layer before writing to the database. No sequence that becomes a contention point under high write loop. Thirdly, UUIDs don't collide across sources. If I ever need to merge data from multiple databases, export records, or shard, UUIDs are safe. Sequential integers from 2 sources will collide. There are 2 real trade-offs to acknowledge. Random UUIDs are 16-byte versus 18 for big int, and random inserts fragment B-tree indexes at my scale, presumably thousands of orders, not millions. Neither matters. There's also an ordering problem. Random UUIDs don't sort by insertion order. Don't design pagination to sort by UUID. Use created at for ordering instead. When index fragmentation or ordering becomes a real concern, UUID v7 solves both. It encodes a millisecond timestamp in the first bits, so it sorts chronologically and fragments indexes much less than v4. For now, UUID v4 with a created at index is the right combination. JSONB blocks, no raw HTML, no cross-site scripting risk. My blog posts don't store HTML. They store structured JSONB blocks. Each block has a type and a content object. A paragraph block, a callout, a heading. When React renders a blog post, it reads the block array and switches on type. 1 React component per block type. No dangerously set inner HTML. No raw HTML from the database. The cross-site scripting protection isn't an afterthought. It's built into the content model. The capability that makes JSONB genuinely powerful here is the gin index and containment queries. 2 examples on the slide where content at is greater than type callout JSONB, all posts containing at least 1 callout block using an inverted index, no full scan. Or content at is greater than type heading content level 2 JSONB, all posts with an H2 heading, path query, no JSONB unpack. A plain text column storing HTML can't do either of these without a full text scan. Full text search, tsvector with weights. Both blog posts and products have a generated FTS column of type tsvector. When content updates, the column regenerates automatically in the same transaction. A gin index on FTS makes search fast. No separate indexing pipeline, no eventual consistency. The generated column uses set weight to assign different weights to different fields. Weight A for the title, weight C for the body text. When you query with tsrank, results with title matches scores higher than the results with only body matches. A search for authentication returns my authentication post at the top, not a product description that mentions authentication is passing. The store keyword means Postgres computes and stores the value at write time rather than computed it on every read. Looking at the comparison table on the right, tsvector wins on index support, title ranking, and stemming. Running matches run. Both handle consistency the same way since tsvector updates happen in the same transaction. Neither handle fuzzy matching. That's the upgrade trigger to Elasticsearch at around 5 million documents. Soft deletes, publishing, and views. Blog posts use deleted at timestamp for soft deletes. Products use a is published flag for staging. The practical risk with soft deletes is shown on the left. Every query that fetches posts must include where deleted at is null and is published is true. Forget it once and deleted content reappears. Forget it in a search query and deleted posts show in results. Forget it in the admin export and deleted data leaks. The fix is a database view, shown on the right. Create, view, visible posts as select, all from notes where deleted is null and is published is true. Any query that uses visible posts instead of notes gets the filter automatically. It's impossible to forget it because it's not there to forget. Direct table access is reversed for admin operations where you want to see everything, including soft deleted rows. The core principle here, the correct path should be the easy path. The view makes the correct query trivially short. The wrong query against the base table requires a deliberate choice. Constraints, correctness, the database enforces. Constraints matter because application code can be bypassed. Migration scripts, manual SQL queries, bugs in application layer, all of these can write data the application code never intended. Constraints cannot be bypassed by any of them. There are 5 constraint types, each with a specific job. Not null on every required column. No orphan rows. Forces explicit intent on every write. Check constraints for ranges. Total sense is greater than equal to 0. Quantity is greater than 0. Invalid values are rejected at the storage layer. Zod validates these in your server actions, but Zod can be bypassed by a migration script. The database cannot. Unique constraints for deduplication. 1 stripe event ID per order. 1 item potency key per operation. 2 concurrent inserts with the same key. Exactly 1 succeeds. This is atomically enforced. Foreign key with on-delete restrict. No orphaned order items if an order is deleted. Restrict surfaces the bugs explicitly rather than silently cascading. And the one worth being specific about, status fields. Don't use text column with Zod validation for your order status. Use a Postgres enum on check constraint. Pending payment and pending payment are different strings. Capital and lowercase, right? The database rejects the wrong case with a clear constraint violation. Zod won't catch a migration script that writes the wrong case. The database will. Migrations, raw SQL, and Expand-Contract. I manage schema changes with raw SQL migrations. The files are kept in my Supabase directory with timestamp names. 3 commands cover the full workflow. Supabase migration new creates a timestamp.sql file in the migration directory. Supabase DB reset applies all migrations locally, giving you a fresh schema on every run. Supabase migration up applies to production inside a transaction. Either the entire migration applies or none of it does. One exception worth knowing. Create index concurrently, which builds an index without locking the table, cannot run inside a transaction. It goes in its own migration file. No transaction wrapper, and it fails midway. You clean it up manually. It goes in its own migration file. There's no transaction wrapper, and if it fails midway, you clean it up manually. For schema changes that could break application code, the right side of the slide shows the expand-contract pattern applied to a column rename. The first phase, add the new column as nullable, write to both old and new, deploy. Old callers are unaffected. Phase 2, backfill all existing rows, verify data integrity. Phase 3, switch all reads to the new column. Monitor for 0 reads on the old one. Phase 4, drop the old column. Breaking changes, risk 0. Never resume a column atomically across a deployment boundary. The window between deploy and migration is always there. What I intentionally kept simple. 5 things I haven't done yet and why each omission is deliberate. Connection pool timing. Supabase PG Bouncer is on by default at the pooler port and I use it. What I haven't done is tune the pool size or pooling mode. That is why I deferred, not the pooling itself. Connection pooling tuning. Supabase PG Bouncer is on by default at the pooler port and I use it. What I haven't done is tune the pool size or the pooling mode. That's what I deferred, not the pooling itself. Read replicas. All queries hit the primary. No read replica routing complexity. No read your writes logic to reason about. Fine at my current scale. CDC and event streaming. Audit logs are written in the same transaction as the operation they record. EMA outbox is pulled by the cron. There is no separate pipeline to operate or monitor. Table sharding. My tables have thousands of rows, not billions. Sharding introduces cross-shard query complexity for zero current benefit. Dedicated caching layer. Index reads are fast enough. One view service to monitor, backup, and reason about. Each of these would be the right decision at larger scale. I'll add them when measurements show I need them, not before. Summary and for client. Let me close with an end-to-end example that shows how these decisions correct. When a user applies a coupon and checks out, 5 tables are touched in a single transaction. Coupons is locked with select for update and the usage count is validated and incremented. Orders is inserted with a UUID status pending payment. Order items is inserted for each line item. Email outbox is inserted with status pending, and order events records creation event. Either all 5 writes succeed together or none of them do. The UUID ensures no ID collision. The check constraint ensures the order total is non-negative. The foreign key constraints ensure product IDs exist. The state machine triggers ensure the state transition is valid. We have 5 key takeaways. UUIDs for public IDs. They're enumeration safe, globally unique, merge safe. Use UUID v7 when index fragmentation or ordering becomes measurable. JSONB plus GIN for flexible content. Type blobs map to React components. Cross-site scripting protection is structural. Containment queries replace full table scans. tsvector with weights. Title matches outrank body matches. Update in the same transaction, no asynchronous pipeline, no eventual consistency. Constraints at the database layer, not null, check, unique, foreign key. These status fields must be enums or check constraints. Zod alone is not enough. Expand contract for schema changes, add new column nullable, backfill, migrate reads, drop old. No atomic rename across a deployment boundary. Unfleshed out thoughts. I'm building a full-stack e-commerce platform for digital products and software services with Next.js and Supabase. If you're designing your own schema and want a second pair of eyes, reach out. I'm open to freelance projects and consulting. The full post is linked in the description below. Complete ER diagram, all code snippets, and the migration file. Next, caching strategies. ISR HTTP cache control headers and what I'd add with Redis. I'll see you there.